Okay, you might highlight this as special topics. Chemical equilibrium. The first one is dealing with the subscript. We've talked about Kc as dealing with the molar concentrations of solutes in solution. But there are other subscripts, such as a Kp value, which deals with partial pressures. So this topic is Kc versus Kp values. Kc deals with molar concentrations, whereas the Kp expression deals with partial pressures of the gases within the reaction. Reaction equation. Okay. For example, if we have a reaction, carbon monoxide as a gas reacting with 3 moles of molecular hydrogen, and this reaches equilibrium at 1200 degrees C, very high temperature kind of thing. Methane is generated in gas form, and H2O is also generated in gas form. The notes give me a Kc value of 3.92 right here. Not a real big number, probably a little more products concentration than there are reactant concentrations, but nevertheless it's a value that you can kind of use for whatever reason you're doing this. Okay? My job is to teach you how to get it, and then if you need it, use it. In writing the Kc expression for this, we have products over reactants, as we have before. So Kc is methane gas. All of it's gas. I'm going to leave for space reasons. Right there. You can write the same expression in terms of partial pressures, which would look like this. Kp, product partial pressures over reactant partial pressures raised to the cube power, or the third power, because hydrogen has a coefficient of 3. So we write partial pressure of CH4, put that in parentheses, H2O, put that in parentheses, and then carbon monoxide, partial pressure of carbon monoxide, and the partial pressure of molecular hydrogen, and that's cubed, like that. It too will give you a number that you interpret as we have before. A lot of products are not so much product in terms of the extent of reaction. The outcome of this still tells you there is not much product. We got a small Kc value, and that's your interpretation. When you do this, you will also get a small Kp value, which tells you the same thing. Now, if given the Kc, which I specified first, you can write a relationship between Kp and Kc that looks like this. And this is derived from the ideal gas law, and I'm not going to go through that. It's in most books, and I'm just going to teach you how to use this expression to obtain a Kp value given a Kc value. Kc, of course, is the 3.92. R value is your gas constant, 0.08206 liter atmospheres per mole Kelvin. We're using gas law R values. As we go through the semester, maybe you know from last semester that R value can exist in other forms. In thermodynamics, is 8.314 joules per mole Kelvin, and one's derived out of the other. But in this one, using partial pressures, remember to use the gas law R value, universal gas constant. Temperature is Kelvin. And you recall Kelvin is equal to degrees C plus 273, just a reminder. Okay, so putting these two in plus a given here. Now, what is the N value? The N value is the change in molar volumes from the reactant, the total molar volumes of the reactant to the product side. When we look at this expression, the coefficient of CO and methane and water are understood to be 1. That also, in terms of gas phase, represents 1 molar volume, Vm, which is the volume occupied by 1 mole of any gas. If you're talking about standard volumes, you would talk about 22.4. And that exists at 0 degrees. But if you change that temperature, you're changing the molar volume. But the definition of molar volume doesn't change. It's just a bigger circle at a higher temperature. But it still has 1 mole of gas in that circle, or volume. Some students think that a molar volume is always 22.4 regardless, and that's not true. Only at 0 degrees Celsius in 1 atmosphere do you have 22.4 liters for any gas. But you raise it to 25 degrees, you may have 24.3 liters. So keep that in mind. I just emphasize that for your benefit in here. So when we talk about molar volumes for one of the components, all we say is this is 1 Vm, whatever the temperature is. We're here with 1200 degrees. We've got a big circle. Okay, and here is 3 molar volumes, 1 molar volume in methane, and again 1 Vm for, well, excuse me, is that it? Yeah, 1, I thought there were 2. 1 molar volume there, okay? The total molar volumes of reactants is 3 plus 1 is 4. So in here I have total 4 Vm total. Over here I have 2 Vm total. Right there. So if I want to calculate delta N for this, I would products minus reactants in molar volumes. That would be 2 Vm minus 4 Vm, which equals a minus 2 molar volumes, a decrease in 2 molar volumes. When using this in the expression here, just put the number, if it's a negative also. So for this particular problem, we can now calculate Kp, which is Kc 3.92, and then I always tell people to do this in parentheses and brackets first, where you have R 0.08206 and 1200 degrees. So that's 1473 Kelvin. And we want to go to a minus 2. One thing I didn't do here is put units in it. Units are important. I don't minimize that, but more important is the magnitude of the number you get, because this is what tells you about the extent of the reaction. Okay, we're going to use the 1200 Kelvin that he used, because I don't have to sit here and calculate all day. And the outcome, 4.04 times 10 to the minus 4. Is the answer. The idea is, what does it mean? It means ain't much product generated. That's all it means, and most of it at equilibrium is reactants. Well, so does the 3.92. It says ain't much generated, and you have mostly reactant at equilibrium. That equation. Okay? R value will be on your reference sheet. Temperature, check it to Kelvin. I'll put a little K down here just to remind you, Kelvin. Hopefully you understand what I mean by molar volumes. Everybody good on that? Yes? Nod, or at least nod? Yeah, okay. Kc will be given. All you have to do is substitute in there. Now I can throw you a curve real quick. I can give you a problem and the Kp value. Solve for Kc, it is identical to what you're looking at, Kp, RT, but change the exponent, delta n, to a negative. It makes it real easy. Okay? A real simple problem. The essence is you can relate partial pressures to concentrations, and they give you numbers that you interpret in the same context. This is derived, just for general information, from the ideal gas law. Most textbooks will present it, but I'm not going to go through all that right now. Is adding reactions to generate a K equilibrium constant. So you're given two reactions, and you add them together, and you apply a rule that I'm going to give you to get the equilibrium constant of the sum of reactions. Sometimes a reaction is not efficient by itself, but you can couple it with another reaction and generate a better outcome. And the ones I'm going to give you is the hydrogen sulfide scrubber reactions. You'll see it when I put these up here. Reaction 1 is CO as a gas plus 3H2 as a gas going to CH4 as a gas plus H2O as a gas, and K for reaction 1 is 3.92. A second reaction is given, methane and hydrogen sulfide, a very poisonous gas, and outcome is carbon disulfide, and that's, at this temperature, gas, plus 4H2 gas, and K2 is 3.3 times 10 to the 4th. So that one moves quite far to the right. And so the outcome that you want to show is you want to scrub and convert this to something that's not dangerous, so to speak. So now we add these two together. Add reactions. We'll come up with carbon monoxide interacting with hydrogen sulfide, and the outcome is carbon disulfide plus water gas plus H2 gas. Okay, so this scrubs not only the carbon monoxide, which is also hazardous, but it scrubs the hydrogen sulfide gas. And you can add these. See, this will cancel, that'll cancel. 3 cancels against the 4, and you still have this and the hydrogen sulfide, carbon disulfide, water, water and hydrogen. Well, now the interest here is what is the equilibrium constant of this, okay? To get the equilibrium constant, this is the rule. For equilibrium constant for adding reactions, it is the product of the constituent reactions. That's the ultimate thing I'm trying to get to. Now, you can write the equilibrium K1 in terms of the reagents and components of reaction 1, and multiply that by the expression, Kc expression or equilibrium expression for the second reaction. Multiply them together, and you will get this result, products over reactants. I'm not going to do that. I'm just going to go straight to this. So we're looking for a K value for reactions 1 and 2. And according to the note, it's K1 times K2 when you're adding reaction together. And we'll hit this again when we get over in solubility product equilibrium and we start talking about what we call complex ion equilibrium. And you will have to add 2 reactions together and multiply the solubility constant values. But here we have 3.92 times 3.3 times 10 to the 4th. The outcome of this is 1.5 times 10 to the 5th. Okay, the next topic is heterogeneous equilibrium, meaning that not all of the components of the reaction are gas phase. You might have a reaction which contains liquids, solids, or both liquids and solids, or all solids in one gas item. And sublimation, you'd go from gas to solid, solid to gas. Here is the essence of this idea. This solid and liquid concentrations are assumed to be constant. Three examples I have here. One is iron, 3 moles of iron in standard state plus 4 moles of water goes to Fe3O4. Anybody know what that is? Okay, good old rust plus 4H2 as gas. We notice that it has a solid and a solid in it, but these 2 components are gas. And when you write your Kc expression, products over reactants will include only those components raised to the power of the coefficient. So in a typical exam problem, you may be given something like this, and you're given data, concentration data for every component in there, and asked to calculate the K value. Well, the concentration data for the solids and liquids you ignore and write your expression and substitute the values for the gas phase only. I'm not going to try to dig up a problem. I'm going to show you how to set these up. And if in any of heterogeneous problems pop up, just extract the concentrations in moles per liter, plug them into the expression you derive, which you should be able to do now, and pick out your answer. Okay? So another couple is, how about one on evaporation of water? I.e., that is, boiling. At boiling, water is in equilibrium with the liquid phase. And so we illustrate that in this context, the gas phase. And if you have to deal with the equilibrium constant, in this particular case, Kc, in this case, deals only with the gas phase and is written H2O gas over 1. Okay? There is no other component on the reactant side, which of course translates to H2O. So that evaporation process depends on the concentration, efficiency of concentration, only on the gas phase concentration. Now, to illustrate the idea of putting that 1 in here, what if we dealt with the condensation of water, just as a contrast? E at dew point. Dew point is that point in which the atmosphere is saturated and cannot hold any more vapor. As a result, we start getting rain, or precipitations, or condensations, or however. Well, what does that mean? That means you're going from a gas to a liquid now. So to represent that process, you're in the gas phase, and you're going down to the H2O, so to speak, liquid phase. You condense it down there. Still products over reactants. And when you write your Kc expression, that's a liquid. What do? You ignore it and you put a 1. So this would be 1 over H2O as a gas, like that. So that is the expression that you would use. The outcome, you just pull the concentration in moles per liter from the problem and put it in. The biggest issue here is, can you write a heterogeneous equilibrium constant and just simply ignore all the solids and liquids and write what's left? Okay? Everybody good on that? Yes?
I wanted to check your number for the sum of reactions. Was that right, or you just picked a number?
Okay. This one is given some data, and you plug it into the expressions. How does that expression tell you which way a reaction will shift? For a given reaction at equilibrium, concentration values are substituted into Kc expression for equilibrium constant. So let's assume the following reaction. Reactants at equilibrium with products. And at equilibrium, EQ, we don't go, we've already gone through the initial and the change and the concentration equilibrium. We don't need a table because the problem is giving you the values at equilibrium. Now, I'm going to leave off units, and this is just a generic type illustration so that you can see how what I'm trying to tell you works. Okay, we've got 7 molar or 7 moles or 7 particles or 7 reactants. Well, at equilibrium, you're going to have 7 products in our example. So the Kc expression is, again, products over reactants, so the forward reaction. And 7 over 7, of course, that gives you a Kc value of 1. Okay? The issue is we don't know which way it's going to go in here. But we have a K value for this problem. It's 1. We know what that is. Now, you don't have to figure, you may have to figure it out. I don't know. Depends on data given. But let's assume that the problem is giving you the K value, Kc value, under the same temperature conditions, temperature pressure. And here's your problem. You still got a Kc. Normal Kc is 1. I can write an expression. Listen to me. I can write an expression of this reaction, but we call it a Q value. It's not a K value any longer. A Q value, or QC value, or QA value, or whatever you're working with. A Q value indicates not at equilibrium. That the reaction is in a condition where it will shift left to right. And what we're trying to do is determine from the numbers which way it'll go. So in this issue, we write Kc as products over reactants. Well, we do the same thing for a QC expression. Products over reactants. And plug in the given numbers based on whatever the problem gives you. And in this case, the products turned out to be 4 over 10, which is equal to 0.4. Is the QC value. And what you want to do is compare this number, QC value, with the 1 and say, which way will it shift? Right or left? If I have this combination. And when I say shift, it'll shift until it establishes new equilibrium. I'm going to give you the other side of the coin too. Reaction, this is case 1 and this is case 2, not at equilibrium. Here again we have reactants and products, and the Kc value is 1. C is in the not equilibrium issue. We'll reverse that. 4 and 10. Let's just say you got more products and reactants this time. So your QC expression for this scenario is still products over reactants. In this case, 10 over 4, which is, well, 2.5. Trying to keep it all on the page. There they are. Start and then insert an inequality, equality, and an inequality pointing in the opposite direction. We look and we see 0.4, and I'm going to put it up here, 0.4 for QC, excuse me, 0.4 for QC, and a Kc is 1.0, where Kc is greater than QC. This one is shifting right after you mix those components together. In the case here, you see that Kc, well, of course, is still 1 right here. But the QC is 2.5 right here. This arrow points to the left, so this will be a left shift. Okay. You can see this. I used to have a zoom on here somewhere. Far. Okay, here's a typical problem that you'll run into. Here, the following reaction is given with an equilibrium constant given. For each of the following compositions, determine if it's going to shift right, shift left, or at equilibrium. If it's the Kc equals Qc, it's at equilibrium. You're already there. So in case here, you'd have nitrous oxide squared, bromine, divided by the nitrosyl bromide squared. Take the values, plug them in, calculate the Q value. Compare it to the 3.07 times 10 to the minus 5, minus 4, excuse me. And decide, well, is Q greater than, less than, or equal to? And use the diagram that I gave you to decide if it goes left or goes right. Here. Oops, wrong ray. There are two very specific kinds of problems here that I want you to know about. And they deal with calculating equilibrium concentration values for a given reaction. Case 1 does not use the quadratic equation. Case 2 does use the quadratic equation. So I'm showing you one of each and why we use them as we do. Okay, if I have in case 1, the reaction initially, let me put it up here, carbon monoxide gas plus H2O gas at 1,000 degrees C goes to CO2 gas plus H2 gas, and Kc equals 0.58. I'm running out of space. 0.58 given. Can you read that? 0.58 on the end down there. Initially, you're going to add 0.2 mole per liter of carbon monoxide gas, 0.02 molar in water gas. And of course, since the reaction hasn't started in that row, it's a CI row, then we're going to enter automatically zeros. Okay? It's not a case of something on the product side like I was doing over here. How does it change through the kinetic region? Well, it goes down by x, up by x, up by x, like that. If I had a 2 in front of it or something, I'd put a 2 times the coefficients. And we come down here to the equilibrium row. and we algebraically add everything together. That's 0.02 minus x, 0.02 minus x. 0 and x is x. This is x right there. So we have our equilibrium variables set up. Now the question is, what is x? Okay? In this particular one, you'd set up a Kc expression, okay, which would be CO2 gas, H2 gas, divided by reactants, carbon monoxide gas, water gas, like that. And substitute the equilibrium numbers. That's what you do this for. You do not substitute the CI. That would be a QC problem if you were throwing in the CI. Okay, this is x times x over 0.02 minus x times 0.02 minus x. Some of you already see where I'm going. So I can simplify this into x squared over 0.02 minus x squared right there. Solve for x. Take the square root of the last term and Kc. So I'm going to pick up this Kc value, 0.58, inner square root, and the square root of x squared over 0.02 minus x squared, like that. This reduces very quickly to 0.76 to equal x over 0.02 minus x. That is one equation can be solved in one unknown. It's linear. And to save us a lot of grief, this comes out x to equal, well, I should put 0.0086 molar. That's what it'll come out to be. Now notice I put a plus minus in there. Okay? Checks. Okay? So that's the concentration, because it's pretty easy to solve throughout the equation. But what happens when you don't get equal amounts of reactants going into the in this case, we have hydrogen iodide, molecular iodide at 458 degrees producing 2 molecules or 2 moles of hydrogen iodide, and you're given a Kc value of 49.7. The problem comes in when you add certain things to the reaction kettle. And in this, you have 1.0 molar of hydrogen and 2.0 molar of iodine thrown into the kettle before you start. These are not equal. So in the change in concentration on the way to equilibrium concentration, again, you apply the changes as shown here and add them to the initial row here, and you get 1 minus x, 2 minus x to simplify, and 2x, like that. This is the data, watch me, this is the data that you plug into the Kc expression. So writing the Kc expression for this, we put 2x squared over hydrogen, which is 1 minus x, and 2 minus x. That's not a linear equation. You can't take square root of that one and calculate x. You have to use, well, the K value is given, 49.7, solve for x. You have to use quadratic equation. And of course that's x equals minus b plus or minus the square root of b squared minus 4ac over 2a. Now, to make a long story short, I worked this out. This expression right here, and this is for ax squared plus bx plus c equals 0. Okay? Everybody knows that, I hope.
That's the final from the bottom.
Very good. All right, so I've simplified this expression to the following based on the numbers that we have there, and this will come out as 0.920x squared plus, well, actually minus on this one, minus 3x plus 2 equals 0. And so in that expression simplifies to that. And applying the quadratic equation, just trying to save us some time. I could play games. 1.84, and this will give us 2.33. Actually, it's a plus or minus 2.33. Oh, and gives us x1, I forgot, and x2 to equal 0.93. Now, which one do you use? Well, if you come back up here and look at the equilibrium row right here and subtract 2.33, 1 minus 2.33 is less than 0. Not allowed. So you would discard that number. You can't have negative concentrations. That's the point. Even though you go through all of this, the point I'm trying to make, everything I've done from that expression to through here is nothing but an algebra class. You should be well aware of that. This is what I'm trying to teach you right here. Which of those two solutions should you use in your K expression up there? Which represents the concentration? Well, if you put this 2.33 in the 1 minus x, you get a negative number. Well, the most you can't go below 1 because that's all you've got in there. Because you started with 1, you go down to a minus whatever the difference is impossible. So the issue is you test it and along your equilibrium row and see if you get any negative numbers. If you get any negative numbers, throw that value out. And the 0.93 will fit and give us reasonable numbers of concentration at equilibrium. Because it reduced to a linear equation and one unknown. And all you do is solve for x, and you can't get an incorrect number. It will fit every time. Well, you'll use this issue. When you put your calculated x in, it has to be above 0. You can't go below the amount that you started with. It can't be negative, in other words. So since 1 minus 2.33 is less than 0, we throw that value out and use the other one.